So students, today you will be looking into experiment number 2. I think last week all of you have done your experiment 1, isn't it? Have you all understood last time's experiment? The um, the implementation, okay, and how we use the K-map, right? So all of you have understood it, isn't it? Can you please unmute and respond?
Yes, sir.
Thank you. Thank you for that response, students. So today we will be moving on to the second one, okay, which is about your adder and subtractor. I think by now you would have come to that point in your theory classes. Have you? Adders and subtractors?
Yes, sir.
Yeah. So basically we use this adders and subtractors for purpose of adding and subtracting. Okay. So we will just look into what are the specifications. Okay. So the experiment is, all of you note down, the experiment is to realize half and full adder, then half and full subtractor using logic gates. Okay. So that's the name of your experiment. All of you make note of it. Then the components required will be your trainer kit, okay, your IC trainer kit, and then you will need ICs 7486, 7408, 7400, 32 and 04. So I think you all know by now what these numbers correspond to, isn't it? Last lab we have seen those, right? So the block diagram is, you will have a half adder, A, B are the inputs, and the outputs are sum and carry. So as usual, you know your 2-bit inputs, which is 0, 0, 0, 1, 1, 0, 1, 1. So 0 plus 0 gives me both sum and carry 0. 0 plus 1 gives me 1 as sum and 0 as carry. The same case with 1 and 0. If I get a 1, 1, then my sum is 0, but carry is getting generated. So the expression, okay, directly it can be written for sum. Okay, you have A bar B plus A B bar. Okay, so that corresponds to your XOR gate. C is equal to the carry is 1, and A and B are high. So directly I can write it as C is equal to AB. Any doubts here, students, up till this point? I want you all to respond.
No, sir.
It won't be single way. Okay, I want it to be in such a way that all of you respond, ask questions. Okay, so that's the way that we have to go about. You just simply sit, I will not know if you have understood. Okay, so you have to be interactive and you have to ask questions if you have not understood, and you can respond, okay, whenever I ask you questions, right? Okay, so once you have these equations, okay, you can see that you can implement it directly using your gates. Now then the numbering, okay, the pin numbering of the gates are important because it will help you in your implementation. Okay, so your 7408, okay, corresponds to your multiplication, which is your AND gate, and 7486 corresponds to your XOR gate. Okay, so A and B are given as your input. So similarly, if I have to represent it, okay, using my universal gates, okay, so this is how you're going to represent, wherein your XOR function, okay, your XOR function is taken care by these 4 gates. Okay, these 4 gates will help us get the XOR function, and this one will help us to get the carry, which is C is equal to AB. Okay, ultimately here you can see that this line is connected here, right? So which means it is multiplying A and B. So what you have to remember here is it's an inverted version, right? It's an inverted version. So what I have to do is I have to put another inverter. So inverter here I can short both the terminals, and whatever is the output I get, my output is actually AB bar here, okay, and then I pass it, then it becomes AB, the bar gets nullified. Okay, so this is about your any doubts yet, students, up till here? Up till here, any
No,
doubts?
sir.
Yeah.
No, sir.
So how will you put up this universal gates? You can use the method. Okay, you can actually convert them, this basic gate to the this special purpose gate to a basic gate. Okay, so which means you will be using an inverter for B bar implementation. Okay, and then for A bar also you'll be using an inverter, and for multiplication you will be using an AND gate. So implement a normal logical diagram here, and once there is a normal logical diagram you can use the bubble method. So in that way you can actually convert your basic gate to universal gates. Okay, so all these are implemented using your NAND gates. Fine. So here, what is the difference between your half adder and full adder? Full adder is an extended version of your half adder, meaning we can take the best use of combination of inputs, which means I can extend the combination of inputs using the full adder. Here I am limited to only A and B, okay, but then here I can extend it to another one, which is C. Okay, so here also my outputs are going to be sum and carry. So since it's 3 input, you all know that it's going to be from 000 to 111. Those are going to be the combinations. And let us see the last case here, okay, where you have 1 plus 1 is actually 0, and then 0 plus 1, it gives me 1. Because of this 1 and 1, 1 plus 1, I am actually getting a carry, which is 1, the same that we saw previously for your half adder. You have 1 plus 1, okay, sum is 0, carry is 1. So to this 0, again I am adding 1, so I get 1, 1. Okay, so I'm getting 1 and 1 here. So I hope you have understood this uh, truth table, right? Any doubts in this section? Any doubts?
No, sir.
No doubts? Can I proceed? Okay.
Yes, sir.
Yeah. Thank you. So once we have the truth table, it's very easy for us to extract data from it. Even here you can use your truth table and put it into a K-map. But since it's very simple here, okay, you really don't have to get into K-map and all those reduction techniques. But in case of your full adder, okay, you will have to get into it. Okay, you will have to make use of your K-map. Okay, so just look for all the high values here, and accordingly you can value your squares. Okay, for example, 0, 1, 2, 3. Okay, so 0, 1, so 1 is high, right? So at 1 it is high. So similarly, take all the values from here and load your K-map. So once your K-map is loaded, you can see that I don't have any option to group them, okay, because there is no pair at all. right? So I will have to just circle them in single and put the equation. So finally I will be getting A is XORed with B and XORed with C. Okay, so that's my final thing that comes up. Okay, and for your carry also, you can actually these ways. Okay, you can put up all the values that you have got into the K map of carry, and here you will get a proper grouping, and it's easy for us to uh, get the final equation here. Okay, fine. So further, this is actually simplified. If you can see here, your AB C in plus C in bar. Okay, then again plus C in AB bar plus A bar B. So this part, I will be taking it as your XOR function. Okay, so that is what I have done here. So once we have these equations, okay, so the next part is easy for us to get the logical circuit. Okay, so once we have the logical circuit, the basic circuit, then we can easily implement. Now there are different ways of implementing your full adder. You can make use of two half adders and an OR gate to implement. Okay, or yeah, so here you have used your pin numbers. Okay, 1 2. Okay, then first and second pin of your AND gate. The output is a third gate. I think yesterday in my last lab, okay, I have given you this pin numbers as well, right? Have you all gone through those pin numbers which I had shared last week?
Yes, sir.
Yeah, so that it will be easy for you to understand as to which are inputs and which are your outputs. Okay, so consequently you can connect to those particular pins, and you can take the inputs and the outputs accordingly. So this is going to be your adder. This is going to be your second half adder. Single, if you see, you just look at this block. Okay. You have an XOR gate and you have an AND gate. So try to compare it with your previous one. It should be the same, right? So it should be the same. So I am making use of two half adders and an OR gate to actually come up with the full adder. If not, we can in fact directly use our XOR gate and implement this. Okay, so directly it can be done, or we can even make use of this half adders and implement it. Okay. So again, here you can convert this to your universal gates. Okay, so if you can observe here carefully, your half adder is let me just annotate so that it becomes easy for you to understand. Right, so this half adder, okay, is actually here. Okay, and this one is available here. Okay. And this one we have converted, okay, for the purpose of carry out. Okay. So this is how you will actually implement it. So as I told you, you can make use of your bubble method, or you can you can use the sometimes they would ask NAND implementation or NOR implementation. Accordingly, there are separate rules for bubbling, and accordingly you can go ahead and um, use those techniques in converting these basic gates. Okay, you can convert them into these universal gates. and you can just have a look here. Okay, I have given it as 7400-3. What does it mean? Is there a pin number called -3, or is there an IC number with that configuration? What are we trying to do here?
It's a sub-series, sir.
No, it is based on the number of pins. Okay, so here in your first 7400, I will use the maximum number of pins. Once there are no pins available, so I will again get back to another different IC. Okay, so this is my first IC, and this is my second IC, and this is my third IC. So which means I'll be using 3 ICs. Okay, I'll be using 3 ICs because with single IC I cannot implement the full thing. Understood?
Yes, sir.
Yeah, because I am
Yes, sir.
making so 4, 1, 2, 10, 13. So almost all have used it up. So similarly here also I'll be using another set of IC. Okay, so that is my second IC, and finally I'll be using another last one. So when you are doing your practicals, you will have to ask for components. Okay, so you will have to know how many ICs that you will need. So once you write it in a slip and then give it, then they would accordingly give you the uh, components. So yeah, so this is about, that was about your adders, and now we will look into subtractors. Okay, so which means here we do have a difference and both instead of sum and carry. Okay, half subtractor and full subtractor. So now if you look at the truth table, 0 0 0 1 1 0 1 1. Okay, you can observe that your difference, okay, difference also has the same equation as that in half adder, right? A XORed with B, so it has the same one. So the only change that is going to happen is with the carry and borrow. Okay, there carry, what was our equation for carry there? C is equal to, yeah, what was the equation? Carry equal to
AB is
AB,
equals
right?
to AB.
AB, yeah. So here you wouldn't find the same thing. Okay, you will find it that it is uh, so based on our table. Okay, yeah. So our borrow is equal to A bar B. So which means we have to um, use an AND gate, as well as I will have to use an inverter for the A bar. Okay, right. So how do we get it? 0 minus 0, 0. Okay, then your 0 minus 1. Okay, so the difference is going to be 1, and the borrow is also going to be 1 because it has a minus, right? Then 1 minus 0, I get 1, and then your borrow is 0. I'm not borrowing anything here. I'm borrowing because the value is very small, right? So I cannot minus something, from 0. So which means I have to take some values. So for that I am borrowing a value. So that is why we are getting high borrow. Similarly here, if I minus 1 minus 1, okay, I get 0 and 0. So students, any doubts in this truth table here as to how we have got these values? Can I proceed?
Yes, sir.
Yeah, okay. Fine. So once we have the equation, okay, the truth table, then the next step is for our implementation. So difference is going to be the same using an XOR gate, right? And then as I mentioned, you'll be using an extra inverter here, okay, which is 7404 series, and the input will be at 1 and output you're going to take at 2. So this is connected to A, so A is coming here and then you get A bar. So A bar, so this is my borrow, A bar into B. And similarly you can convert this to your um, universal gates. So again here you can see I have used one IC for this implementation, and the second one here for borrow out. Okay, for difference one I have used, and for borrow I have used another IC. So that's why you see this hyphen 2. Okay. So extending the capabilities of your subtractor, we will be um, learning about full subtractor. So here also you have difference and borrow, just that you have borrow out and borrow in. Okay. So our 3-bit combination is going to happen here from 000 to 111. Okay, and we will obtain the values for difference and borrow. So we will see one of the case here, 0 minus 1. Okay, so which means I have to borrow to minus this. Okay, so which is 1. 0 minus 1 with borrow 1, the difference is 1. Then again 1 minus 1 gives me 0. Okay, so this is how I get for 0 double 1, I get 0 1. That's my difference and borrow. So that case is actually different when we look at triple one. Okay, 1 minus 1 is 0. Okay, and now I have to minus 0 and your 1. Okay, so which means I'll have to it is not possible for me, so I have to borrow. Okay, so it becomes you will accordingly get your difference and borrow. So once we have this truth table, we have seen previously, truth table, it's easy for us to get a K-map. That is, we load these values into K-map in the particular weighted squares, and accordingly we get the expressions for difference and borrow. Okay, so for difference it's going to be the same equation that we used for our full subtractor, full adder, and full subtractor are going to be the same, and here borrow is going to change. So here also we can use two half subtractors for the implementation of full subtractor. Okay, two half subtractors and an OR gate. So internally, if I see, okay, this is my same representation of half subtractor, right? So this is my first half subtractor, and this is my second half subtractor. Convert them to the basic gates, and then you can use the bubbling method for the implementation of your uh, universal gate using NAND. So here is going to be your first half subtractor, and here is will be your second half subtractor, and finally we'll be taking up the values here. So you can see -1, okay, -2, and -3. So 3 ICs I'll be using for its implementation. Okay, so any doubts here, students? Any doubts with whatever we discussed so far?